Stand at the edge of the port of Los Angeles or the bustling docks of Long Beach, and you will witness a scene that defies basic human intuition. Towering above the waterline, casting shadows that engulf entire warehouse districts, are the leviathans of the modern age. These are the ultra-large container vessels, engineering marvels of the 21st century that serve as the beating heart of the global economy. They stretch out over a quarter of a mile in length, rivaling the height of the Empire State Building if stood end to end. On their vast decks, they carry an unimaginable burden, upward of 24,000 steel shipping containers, stacked like massive, multicolored building blocks. These containers hold everything that defines modern American life. From the high-end microchips and flat-screen televisions destined for electronic stores, to the automotive parts keeping Detroit assembly lines moving, to the millions of tons of textiles and everyday consumer goods lining retail shelves across the nation. When you look at one of these colossal structures, fully loaded and sitting deep in the water, a fundamental question immediately confronts the logical mind. How does a massive wall of steel, weighing well over 250,000 tons, simply float? More importantly, how does it carry a towering mountain of cargo through the most violent, unforgiving environments on Earth without snapping in half, capsizing or plunging to the bottom of the ocean? The answer is not magic, nor is it a simple matter of having a big enough engine. The survival and efficiency of these mega ships rely on a symphony of extreme physics, cutting-edge material science, brilliant mathematical modeling, and a highly complex logistical ballet that operates completely hidden from the public eye. To unravel this monumental mystery, we must first confront the fundamental physics that govern our oceans. Over 2,000 years ago, the ancient Greek mathematician Archimedes stepped into a bath and made a discovery that would forever change the trajectory of human navigation. He realized that any object, wholly or partially immersed in a fluid, is buoyed up by a force equal to the weight of the fluid that is displaced by the object. This is the absolute foundation of naval architecture. For a modern megaship to float, it must displace a volume of seawater that weighs exactly as much as the ship itself and every single piece of cargo it carries. Imagine a massive steel box dropped into a swimming pool. If the box is solid steel, it sinks like a stone because the volume of water it displaces weighs far less than the solid steel itself. But a container ship is not a solid block of metal. It is essentially a meticulously designed hollow steel shell. Despite the staggering weight of the engines, the fuel, the structural framing, and the 24,000 shipping containers, the vast interior volume of the ship's hull is mostly filled with empty space and air. Because air is incredibly light, the overall average density of the entire loaded ship is actually less than the density of the salt water it rests in. When a vessel like the MSC Arena or the Ever Given is fully loaded, its colossal weight pushes the hull deep into the ocean. The distance from the waterline to the lowest point of the hull, known as the keel, is called the draft. On the largest ships, this draft can reach over 50 feet, meaning a 5-story building could be submerged entirely underwater just to support the cargo above. The ship will continue to sink into the ocean until it has pushed aside roughly 250,000 tons of seawater. At that exact moment of equilibrium, the immense upward pressure of the ocean matches the downward pull of gravity, and the Titan achieves buoyancy. But floating in a calm harbor is one thing. Surviving a brutal winter storm in the middle of the North Pacific is an entirely different engineering challenge. Many people hold a dangerous misconception about how ships are built. They imagine a rigid, unyielding fortress of steel fighting against the waves. In reality, rigidity is the enemy of maritime survival. If a vessel stretching 1,300 feet long were perfectly stiff, the immense, uneven forces of ocean swells would cause the steel to fracture and tear. When a megaship encounters a massive rogue wave, the bow is pushed violently upward, while the stern might be suspended over the trough of another wave. This creates a terrifying structural condition, known as hogging and sagging. Millions of pounds of stress are concentrated directly on the middle of the ship's hull. To survive this, naval architects designed the massive steel girders and the hull plating to flex and bend. Modern marine-grade high-tensile steel is used in critical stress points. This specialized steel allows the ship to physically warp and twist as it rides over ocean swells, absorbing and dissipating the kinetic energy of the storm rather than resisting it. If you were to stand in the long internal corridors of a container ship during a heavy storm, you could actually see and hear the massive steel walls groaning and bending around you. a terrifying but completely calculated behavior that keeps the vessel from snapping in two. Furthermore, the hull is not just a single layer of metal protecting the cargo from the abyss. Modern megaships are built with double hulls. This means there is an outer skin of steel in direct contact with the ocean, and an inner skin of steel protecting the cargo holds and fuel tanks, separated by several feet of empty space. If the ship strikes a submerged reef or collides with another vessel, tearing a gash in the outer plating, the inner hull remains intact, preventing catastrophic flooding and catastrophic oil spills. The lower sections of the ship are also divided into numerous watertight compartments, separated by massive steel bulkheads. If the ocean breaches one section, heavy watertight doors seal shut, confining the flood to a single area and allowing the ship to maintain its buoyancy and limp to a safe port. The shape of the hull itself is a masterpiece of fluid dynamics. At the very front of the ship, just below the waterline, sits a massive bulbous protrusion known as the bulbous bow. To the untrained eye, it looks strange, almost like a massive torpedo attached to the front of the vessel. However, this structure is critical for fuel efficiency and stability. As a ship moves forward, it naturally pushes water ahead of it, creating a massive bow wave. This wave creates severe drag, forcing the engines to work harder and burn significantly more fuel. The bulbous bow is perfectly calculated to create its own separate wave right at the front of the ship. The trough of the wave created by the bulb aligns exactly with the crest of the wave created by the ship's main hull. Through the principle of destructive interference, the two waves cancel each other out, drastically reducing the resistance against the ship and allowing it to slice smoothly through the ocean. Yet, understanding how the ship floats and survives the structural stress is only half of the equation. The most critical factor in keeping a megaship upright is the meticulous mathematical management of its center of gravity. A container ship is uniquely top-heavy compared to oil tankers or bulk carriers. The cargo is stacked in massive towers high above the main deck, acting like a giant sail catching the wind and drastically raising the vessel's center of gravity. If you stack too many heavy boxes on the top, the ship becomes top-heavy and will violently roll back and forth in the waves, a terrifying phenomenon that can easily snap the lashings holding the containers, sending millions of dollars of cargo plunging into the sea. If the center of gravity is too low, the ship becomes overly stiff, snapping violently back up right after a wave, which can cause severe structural damage and injure the crew. If the weight is unbalanced from left to right, the ship will sail with a dangerous list, making navigation nearly impossible. Therefore, the placement of every single one of the 24,000 containers is calculated by advanced supercomputers days before the ship even arrives at the port. The cargo planners must account for the exact weight of every steel box. Heavy containers, filled with machinery or raw materials, are strategically lowered deep into the cavernous holds of the ship, resting as close to the keel as possible. Lighter containers, filled with electronics, clothing, or plastic goods, are stacked on the higher tiers above the deck. But cargo is only one part of the balancing act. As a ship travels from Shanghai to Los Angeles, it continuously burns through thousands of tons of heavy fuel oil. As the fuel tanks empty, the bottom of the ship becomes lighter, which inherently raises the ship's center of gravity and severely compromises its stability. To counteract this, every megaship is equipped with a vast, highly complex network of ballast tanks built into the double hull. These cavernous steel chambers can hold tens of thousands of tons of raw seawater. Deep inside the engine room, massive industrial pumps, capable of moving thousands of gallons per minute, are constantly at work. As fuel is consumed, the chief officer opens heavy hydraulic valves, allowing the ocean to flood into the lowest ballast tanks. This artificially adds massive weight to the absolute bottom of the ship, forcing the center of gravity back down and keeping the vessel safely anchored in the water. Furthermore, if rough seas or high winds cause the ship to lean heavily to the starboard side, the automated ballast control system instantly shifts thousands of tons of water from the starboard tanks over to the portside tanks, acting as a massive counterweight to forcibly pull the ship back to an upright, even keel. All of this structural integrity and dynamic stability is pushed through the water by what is arguably the most impressive piece of moving machinery constructed by human hands. Deep in the aft section of the ship, sitting at the bottom of a multi-story engine room, is a two-stroke, low-speed turbocharged diesel engine. The scale of this power plant is difficult to comprehend. It stands over 5 stories tall and weighs well over 2,000 tons. The massive steel pistons alone weigh over 5 tons each, traveling up and down inside cylinders that are wide enough for a grown man to comfortably stand inside. Unlike the high-revving engines in a car, these colossal marine engines operate at a very low rhythmic speed, usually turning at a maximum of around 80 to 100 revolutions per minute. At this speed, the engine generates an absolutely mind-bending amount of torque, producing upwards of 110,000 horsepower. This immense rotational force is transferred through a massive steel propeller shaft, thicker than a large oak tree, turning a single bronze propeller that is over 30 feet in diameter. Every time those massive propeller blades bite into the dense seawater, they push 250,000 tons of steel and cargo forward at a cruising speed of roughly 25 miles per hour. While environmentalists rightly point out that maritime shipping contributes heavily to global emissions, the raw mathematics of logistics paint a different picture regarding efficiency, because a single megaship can carry the equivalent cargo of over 12,000 heavy-duty trucks. The amount of fuel burned per ton of cargo moved is astronomically low. It remains, by a wide margin, the most energy-efficient method of transporting physical goods across the face of the Earth. Without these massive engines and their hyper-efficient fuel consumption, the entire concept of globalization, affordable electronics, accessible foreign goods, and just-in-time manufacturing would instantly collapse. This entire floating citadel is operated by a shockingly small crew. A modern ultra-large container vessel usually sails with a complement of just 20 to 25 human beings. The captain, the navigational officers, the engineering staff, and the deckhands are responsible for a machine worth hundreds of millions of dollars, carrying cargo worth billions. This massive reduction in manpower from the sailing days of old is only possible through total automation. The command bridge, perched high above the stacks of containers, resembles the flight deck of a spaceship rather than a traditional ship's wheelhouse. The navigation officers monitor a complex array of radar screens, electronic charting systems, and dynamic positioning computers. The ship navigates along digital highways using high-precision GPS and GLONASS satellite data to track its position down to the millimeter. In the open ocean, the autopilot systems take absolute control. Microprocessors continuously read data from weather satellites, analyzing approaching storm fronts, wind speeds, and wave heights. The computers make microscopic adjustments to the massive rudder, compensating for ocean currents and wind drift, holding the colossal vessel perfectly on course while burning the least amount of fuel possible. Yet, for all the titanium, high tensile steel, and advanced supercomputing power, the entire system is profoundly fragile. The margin for error when operating a 250,000-ton vessel is virtually zero. Out in the deep ocean, the greatest threat is a phenomenon known as parametric rolling. If a ship encounters a specific pattern of waves that perfectly matches the natural roll frequency of the vessel's hull, a terrifying chain reaction begins. The ship will start to sway from side to side. With each passing wave, the angle of the roll violently increases. Within minutes, a megaship can be rolling over 40 degrees to each side. The structural lashings holding the massive towers of containers reach their breaking point. Steel cables snap like guitar strings, and entire stacks of containers, weighing hundreds of tons, collapse and plunge into the raging sea. Every year, thousands of containers are lost to the deep ocean, creating navigational hazards and environmental crises, a stark reminder that the ocean always has the final say. The danger becomes even more acute when these titans of the sea approach land. The most perilous moments of any voyage do not happen in the deep Pacific, but in the narrow, shallow choke points of global trade. Navigating the Panama Canal, the Strait of Malacca, or the Suez Canal requires a level of precision that pushes the limits of human capability. When a megaship enters a narrow canal, the immense volume of water displaced by its hull is forced into a confined space. This creates a terrifying hydrodynamic phenomenon known as the bank effect. As the ship moves forward, the water pressure builds massively between the bow of the ship and the canal bank, violently pushing the front of the ship away from the shore. Simultaneously, the massive propeller at the rear creates a powerful suction effect, pulling the stern of the ship dangerously close to the rocky embankment. The pilots and captains must constantly fight these massive invisible forces, constantly adjusting the rudder and engine speed to keep the colossal vessel perfectly centered, in a channel that might only be a few dozen feet wider than the ship itself. On March 23, 2021, the world witnessed exactly what happens when this delicate balance fails. The Ever Given, a megaship carrying 20,000 containers, was transiting the Suez Canal during a severe sandstorm. Gale force winds battered the towering wall of containers, acting like a massive sail that overwhelmed the ship's steering capabilities. Caught in the grip of the bank effect and the blinding wind, the captain lost control. The massive bulbous boat drove deep into the eastern bank of the canal, and the stern swung around, embedding itself in the western wall. In a matter of seconds, 400 meters of steel effectively barricaded the most important maritime artery on the planet. The incident caused a catastrophic traffic jam of over 400 ships. Global supply chains immediately began to hemorrhage. Billions of dollars in global trade were frozen every single day. The ship remained stuck. Factories in Europe halted production, waiting for components from Asia. Retailers in the United States panicked as their inventory sat anchored in the Red Sea. It took nearly a week, utilizing a fleet of the world's most powerful tugboats and massive dredging operations to finally free the vessel. That single event laid bare a terrifying reality. Our modern, highly advanced civilization, with its instant communication and high-speed data networks, is fundamentally dependent on the physical movement of steel boxes across water. The entire apparatus of modern consumerism rests on the shoulders of these megaships. The next time you walk through a sprawling American superstore or open a package that arrived perfectly on time, take a moment to consider the journey of those goods. Consider the brilliant minds that manipulated the laws of physics, utilizing the principles of Archimedes to make 250,000 tons of steel float. Consider the immense, roaring two-stroke engine burning thousands of gallons of heavy fuel to conquer the vast expanse of the Pacific. Consider the 20 weary sailors standing watch in the dead of night, fighting rogue waves and hurricane-force winds, relying on the careful balance of ballast water to keep them from capsizing into the dark abyss. The mega container ship is not just a vehicle. It is a floating city of steel, an undisputed triumph of human engineering, and the silent, unsung beast of burden that carries the modern world on its shoulders. They are the true arteries of globalization, quietly executing miracles of physics every single hour of every single day, completely out of sight, yet impacting the lives of every human being on the planet.